Hello everyone, my name is Kaelen Findlay, and I'm a kinesiology student at the University of Alberta. And this summer, I'm currently completing a scoping review on the current assessment and diagnostic telemedicine technology for different shoulder pathologies at the Rehabilitation Robotics Lab under the Tele Rehab 2.0 project. So before getting into the review, I'll give you a little bit of background on telerehab. So the goal is to expand equitable rehabilitation access to Albertans, especially those living in remote areas of the province. Those living in rural settings often have less access to specialists and are required to take on greater traveling and possibly childcare expenses, and an overall diminished work productivity and wages due to these extra barriers when compared to those who live in an urban hub. So therefore, I took on a scoping review to map the literature on what we know about this topic and to identify emerging information and technologies and gaps in knowledge to guide new areas that telerehab can expand into, or further research for equitable access to shoulder assessments and evaluations. So I'll briefly go over my inclusion and exclusion criteria I used in the review. So in terms of inclusion, if the studies were performed in ambulatory, clinical, and home settings, they were included, as long as the technology was specifically made for telemedicine or it could be used for telemedicine in the future. And as well as portable and wireless devices that could telemonitor patients throughout the day during physical activity and acts of daily living outside of the laboratory settings. And lastly, the technology must have either a diagnostic capability of shoulder pathologies or have an assessment portion that could aid in a future diagnosis. And then in terms of exclusion criteria, no smartphone applications such as goniometer apps were allowed, with the exception of streaming platforms like FaceTime, and as well as any tele-rehabilitation devices, as they don't necessarily match the objective of this review. But if they had an assessment capability, then it would be included. And lastly, no stroke or arthroplasty patients. The telerehab project already has existing projects targeted in those populations. And so I'll briefly describe my search strategy that I used to identify relevant articles. And a librarian was consulted in order to decide which databases were best to utilize, and a finalization of the search strategy as well as key terms. So a comprehensive search was conducted on Medline, PubMed, and Scopus, as well as a grade literature search and PubMed mesh terms. And on the screen, you can see the keywords that I used in my search strategy. And using the John W. Scott template, I searched the individual sets together, first using the or and then the and to identify the overlap and the relevant studies on this topic. So the search strategy initially resulted in 873 results, and after a brief scan, 218 studies were then deemed relevant based on the inclusion and exclusion criteria. And after removing duplicates, 165 studies moved into the title and abstract screening, and which resulted in 148 studies moving into the full text review. And so upon completion, 41 studies were deemed relevant for this review, and they were generated from 13 different countries and published from 2002 up until 2021. However, the bulk of the studies were published from 2015 until 2021. And after a formal data extraction, 5 core technologies were identified, and this included the Microsoft Kinect, inertial measurement units, or IMUs, and portable sensors, and video conference platforms, teleultrasound or teleradiology, and other applications. So the first is the Microsoft Kinect, and it was originally built for the Xbox gaming console, but it became compatible with the Windows PC, which created opportunities for add-ons and various software manipulations, and it can essentially sense people's movements and voices. And the Kinect is a popular device for telemedicine, as it can assess shoulder kinematics and range of motion, and is commonly compared to the gold standard, which is the clinical goniometer. And of the studies included, the primary outcomes were assessing validity and reliability of the device when measuring shoulder kinematics, range of motion, and reachable workplace, as well as the overall benefits and limitations of the Kinect. And additionally, these studies, the Connect measured non-pathologic shoulders, as well as dystrophinopathy and non-pathologic shoulders. However, adhesive cupitis. But the majority of the assessments were completed in non-pathological shoulders. And then moving into the IMUs. So an IMU is a small and portable device that's available both wired and wireless, and are typically made of a 3D gyroscope, an accelerometer, and a magnometer. And they can be used on their own as the manufacturer designed, or can be equipped with different algorithms to make a device applicable to the setting of desired use. And for example, one study looked at the coupling of an IMU sensor with virtual reality to measure shoulder kinematics. And as well, you can see on the screen IMUs being used in a wearable tracking suit. So they really can be applied to a whole variety of uses. And the IMU's measurement outcomes included validity and reliability of the measurement of shoulders in physical activity and acts of daily living, as well as joint kinematics and shoulder evaluation within a standardized protocol. And in terms of shoulder pathologies, again, the majority of the studies were performed in non-pathologic shoulders. However, adhesive cupitis and brachial plexus injury were also explored. And then moving into video conference platforms. This can either be performed synchronously or asynchronously. And the primary outcomes for these studies were the practicality of real-time consultations, diagnostic effectiveness, and validity and reliability, and overall a standardization of virtual orthopedic and musculoskeletal shoulder exams compared to the standard in-person evaluations, such as the STAT shoulder exam. And so these platforms are more intended for consultations and physical evaluations of the shoulder, rather than an objective measurement of joint kinematics or range of motion, as we saw with the Connect and IMUs. And then now moving into tele-ultrasound and radiology. 2 studies focused on the use of a portable ultrasound to assess shoulder instability and a musculoskeletal evaluation from a remote location. And the primary outcomes were overall quality and transmission of the exams for interpretation by remote specialists. And probably the most interesting study I found in the review, it was based on a portable ultrasound being used on the International Space Station. So they had an astronaut perform a shoulder exam using the portable device with a sonographer located at NASA, and they were relaying information back and forth. And the sonographer was instructing how to do the exam, and they basically summarized that we can apply it into space, so we can easily apply it into a telemedicine context. And then leading into teleradiology, one study was included, and it was a systematic review that investigated the reliability, validity, cost effectiveness, and feasibility of detecting shoulder injuries. And then lastly, but not least, other applications. So 3 additional devices were included in this review: a force sensing device that can measure isometric strength of the upper limb, and a video conference goniometer that measures the range of motion and strength of the shoulder joint, and a 3D gyroscope that assesses shoulder mobility. And all 3 investigated the validity and reliability of these devices, but the 3D gyroscope and force sensing device were studied again in non-pathologic shoulders, and while the video conference goniometer assessed older homebound adults. And then so leading into the discussion section, I was able to identify 3 major findings, and this included future research, standardization of protocol, and the advantages and limitations of telemedicine. So first is the future research. So there is a large amount of future research that needs to be conducted in this field of study. Telemedicine is very much in its infancy and is overall under-researched, but has a tremendous amount of potential. And telemedicine research was obviously underway prior to the pandemic, but many of the papers included in this review discussed the need for telemedicine research as a result of COVID-19, and that it's essentially more important than ever to look into. And the studies included in this review were generally in agreement that the devices are accurate and reliable in the settings that they were performed in, but they require lots of more investigation in this prior to clinical implementation in terms of larger sample sizes and across more contexts and settings, as many of the included papers were pilot studies. And specifically, future work needs to capture a greater range of shoulder pathologies and investigate how these devices measure them, as the majority were evaluated on non-pathologic shoulders. And secondly, there was a consistent call for the standardization of protocol from all core technologies because it would increase the validity and reliability of the results and measurements, and specifically concurrent validity because it's important in telemedicine devices when compared to the in-person evaluation equivalent to ensure that you're getting equally valid outcomes despite the setting. And then lastly, moving into the advantages and limitations I identified. So the main advantage reported was the time effectiveness the cost and time effectiveness of many telemedicine devices, as they were a cheaper alternative compared to the gold standard measurements, such as motion-based marker systems like OptoTrack and VidCon, which are relatively expensive and can only really be used in clinical environments just due to the space and the elaborate setup required. And there's also a potential advantage for using a device to measure joint kinematics and range of motion in terms of intra and inter-tester reliability, as it could provide a more objective measure that is less influenced by possible human error. And lastly, a video conference goniometer device I mentioned earlier. The device comes in two different modes. One is the hospital mode, where it can be used as a bedside workstation. And then there's the patient mode, which it's a bit more user-friendly and used in the home. And the advantage that they reported was, first, it's interchangeable with the universal goniometer, but it also comes with a computerized library of past assessments. So it's all recorded in one place, which can definitely be utilized and keep track of information in a way that a traditional goniometer just can't do. And however, the main limitations reported, again, is the lack of research and protocol in this subject area, as well as the user usability of the devices. So if patients are unfamiliar with the technology, it can be a bit more stressful and time consuming. And interestingly, one study reported that there may be a reduced psychological benefit to no face-to-face interaction with practitioner, especially if the evaluation is in the home. And video conference may be less useful in patients who haven't met the clinician for the first time, as they haven't built that type of rapport yet, and they might be overall less confident in the treatment or diagnosis. So that is the end of my presentation. Thank you everyone for listening. I can now open the floor up to any questions, and if anyone would like to see my reference list, please let me know and I can email it out to you after today's presentation.
Thanks, Kaelen. We'll hold the questions until the end. And we'll have Pradipika give her talk first, and we'll go from there.
Awesome.
And if you are able to send your reference list to Laura and she can circulate it, that would be fabulous.
No problem. Thank you.
Pradipika, the floor is yours.
Thank you, Kaelen, for your talk on telemedicine. I'm Pradipika, and I'm going to talk about a smart headband for jaw rehabilitation applications. So I'm supervised between Dr. Hyung Jung Chung from Chemical and Materials Engineering, Dr. Patricia Dolos from Human Ecology, and Dr. Daniel Alto from Rehabilitation Medicine. So this is a project that I've been working on for the past 2 years as a part of my master's thesis. So I would like to give a bit of a background about the work. So we have a lot of head and neck cancer patients who undergo surgery during their cancer treatment. There's also people who have oral prostheses due to either old age or athletes due to injuries. So what happens due to this is that due to this surgery is that there's a loss of sensation of texture as well as pressure exerted during daily chewing while they're processing their food. And as a result of this, their chewing forces can go up to 700 newtons. And I've seen that even in case of molars, the forces could go up to 1,000 to 1,300 newtons, which leads to a breakage of these oral prostheses that are inserted into the jaws of the patients. So the consequence is usually a loss of teeth as well as parts of the tongue. So they end up biting too hard and they lose their teeth as well as parts of the tongue. So we have come up with a biofeedback system that consists of a smart oral prosthesis as well as a smart textile. So the smart oral prosthesis would contain sensors that sense the force as well as the texture, and this will communicate wirelessly with the smart textile. And the smart textile will then provide feedback signals to the skin in terms of vibration. So I want to give a little bit of an introduction about smart textiles. So these are textiles that can sense, respond, and react to stimuli. They have been used in healthcare applications since 1988, and they can be made into different shapes and sizes. And they're also conductive. And interestingly, a lot of traditional textile methods like knitting, embroidery, and weaving can be used in order to integrate electronic components into the textile structure. So usually these textile structures have sensors, actuators, and methods of communication, data storage, as well as data processing. The requirements for the smart garment that we have is that it should be able to provide biofeedback. It should be able to provide the right amount of pressure for stimulating the skin. It must be conductive, breathable, as well as washable. So I want to talk a little bit about biofeedback. So there's different kinds of biofeedback that can be given in terms of electrical, optical, mechanical methods. We chose a method called vibrotactile feedback, which is less invasive and has less complications when compared to electrical stimulation, where there's a risk of electrocution. So there's different methods, and of course, because we are using the skin to provide these this vibrotactile feedback, because skin is the largest organ in the body, a sensory organ in the body. There's lots of sites to provide this feedback, so that's a major advantage as well. And there's different methods to even provide vibrotactile feedback, like electromagnetic, piezoelectric, pneumatic feedback, etc. As you can see in the graph here, we are taking advantage of Pacinian corpuscle cells in the skin, which usually have a very less, which require a less amount of displacement of the skin in the frequency range of 200 to 250 hertz. So you'll hear me talk a lot about the 250 hertz frequencies in my latest studies as well. So for the application, we use piezoelectric actuators. So these actuators are able to convert electrical energy into mechanical energy, and they are able to mechanically stimulate the skin using tactile stimulation or vibrotactile stimulation. These actuators are advantageous because we are able to control their frequency as well as amplitude of vibration. And the actuators are also easily integrated with different programming platforms like MATLAB, Python, etc. So in order to, once we zeroed in on the actuator that we wanted to use, we wanted to study how it's behaving. So we use an instrument called the laser Doppler vibrometer in order to study the vibrational characteristics of the piezo actuator. Here you can see a schematic for the experimental setup, where you can see the actuator, which is connecting to a board and then to the computer. So the computer sends different kinds of signals. In this case, we use sinusoidal as well as food texture signals. And it helps in understanding how we are able to control the actuator and how it's behaving when we are sending these input signals. And it also helped me to design some of the human perception studies that I will be talking about later. So I wanted to talk a little bit about the laser Doppler vibrometer. So it consists of a laser that splits the beam splits the laser beam into the reference beam as well as the measurement beam. The reference beam goes towards the mirror and then towards the back cell and towards the detector, and then the measurement beam usually goes towards the lens and then towards the sample. So the way that this works is that when the sample or the actuator is vibrating, the light is deflected in different directions, which is then detected by the photodetector, and those signals are captured and we study those signals. So some of the tests that we did with the piezo actuator and the LDV were that change in displacement according to the distance. So we wanted to see how the vibration characteristics differ when we go from the center of the piezoelectric actuator towards the edge. For this experiment, we used an amplitude of 0.1 and 0.5 250 Hertz sinusoidal signals in the study. So as we move from the center, the displacement produced by the actuator actually decreases. So that was our conclusion. And for the displacement versus amplitude study, we wanted to see how the displacement versus amplitude characteristics change when compared to the edge and the center, as well as in the middle, in between those 2 points. So we observed that once we increase the input amplitude, which corresponds to the input voltage that's being provided to the piezo actuator, there is an increased output displacement, which is very helpful when providing feedback signals in terms of chewing, because if they're chewing with more force, we could give a signal that's more intense to let them know that, hey, you're chewing with too much force, you need to slow it down. There was also a study conducted with food textures. So we had food textures like cranberry, toast, cookie, and banana that were inputted. And these are the output signals. So we wanted to see that whatever input signals we are giving match the output signals, which we were able to observe in terms of the signals obtained from the LDV. So that was a successful study as well. Once we studied the vibrational characteristics of the piezoelectric actuator, we wanted to go ahead and look into the design of the smart garment. We wanted this smart garment to be washable, conductive, and as well as stretchable, etc. So we went ahead and formed like a Velcro structure where one side of the Velcro patch is sewed into the headband and the other side has an adhesive patch, which then attaches to the piezoelectric actuators. So here you can see 3 different actuators. This is because we also want to provide spatial information to these participants, depending on what events are going in which part of the mouth as well. So these 3 different actuators are attached to the headband using adhesive patches. And when a washing has to be done, the patients can strip off these electronic components and then throw the headband into the wash. And so that's a washable structure. We use normal copper wires for providing conductivity and power to the actuators. And it's also able to provide the right amount of pressure because we made an adjustable headband system that could be adjusted depending on patients' head sizes and shapes. And one of the main highlights of this talk is that it can be used, this device can be used remotely by these patients in the comfort of their homes, as well as in restaurants, because we took into account the social aspect of the device as well, because we didn't want these patients to feel awkward while using the device in social settings. So the next study was that of a human perception study. So this study is designed for human participants. However, I was not able to conduct it due to COVID restrictions. Currently, the results that I'm showing, these tests were just conducted on me and my supervisors. So we used a method of psychophysics, which is an area of study where mathematical relationships are formed between the stimuli that's provided to humans, as well as how we are perceiving those stimuli. So a method of psychophysics was used for the analysis of the data. And then this helps in understanding the ability of the smart garment to provide stimuli. For this study, we have 3 different experiments. The first is the sequential actuation algorithm. The second is the just noticeable difference algorithm. And then the third would be the texture analysis. For this experimental design of the sequential actuation algorithm, the aim is to find the spatial differentiation among different participants. So we have two cases among three different actuators. Case one would have one actuator vibrating, whereas case two would have two of the three actuators vibrating. And these two cases are presented randomly to the user. And the user has to answer if they're feeling one or two actuators. So this helps us in understanding how much distance there should be between two different actuators for them to be felt as two different vibrational units. The second experiment was the just noticeable difference in amplitude. So the aim was to find how much the difference in amplitude there should be between two different signals for them to be perceived as two different amplitudes. So in this experiment, we used one actuator and two signals were presented to the user, one after the other. And there was also a method of weighted up-down that was used, which is an adaptive algorithm, which I'll be talking about in the next slide. So in the just noticeable difference experiments, signal 1 and 2 are presented to the user one after the other with an amplitude difference called amp diff. And then the user has to answer which one is more intense. Now, if the answer is correct, the new amplitude difference becomes amplitude into 2 to the power 1 by minus 1 by 3. And if it's incorrect, the amplitude difference increases. So that kind of makes the algorithm more adaptive. And once you keep answering correct, it becomes more harder for users. So then we hit that point where it becomes then harder to answer, and then the answers become incorrect again. And that sort of, goes on till the end of the experiment. So these answers are then recorded and analyzed. For the analysis, we used a method called logistic regression using R programming language. And we wanted to find the X75 value. That's the value for difference in amplitude for the answer to be correct 75% of the time. So that's something that we got from the algorithm which we are using that I was talking about. And after the experiment, we found an average of 5.34, which is pretty good and gives us a good range to play with in terms of different amplitudes that can be provided to these patients. For the third experiment, we wanted to see if the patients are able to identify different food textures. So we used a method of ABX method of delivery. So for example, A would be a signal from banana and B would correspond to that of cranberry, and X would be either banana or cranberry, and the user has to answer if X was similar to A or B. So for this experiment, we used different food textures called namely toast, banana, and cranberry. And the overall correct percentage was seen to be more than 50%. That's more than guess, which is considered to be successful. And we also saw that they were able to distinguish between different food textures. So this concludes the three parts of my experiment. So I would like to move on to the move on to the next study. So the next study was aimed to find the sensitivity of the actuators as well as the smart garments towards the skin. So in this study, we have 250 Hertz sinusoidal signals of 500 milliseconds, and the user is asked to respond as soon as they are able to sense a signal. So we've performed these signals on the fingertip as well as the forehead, and the acceptable threshold is usually 1 second for the response. And it gives us an idea of the amount of amplitude that we are able to play with in terms of delivering signals. And it was also clear from this experiment that the lower the amplitude, the higher was the time to sort of respond to the signal. So as a conclusion, I would like to say that we devised a biofeedback system in order to provide feedback to patients in terms of the texture that they are chewing, and as well as the force that is being exerted in the jaw. For this, we use piezoelectric actuators, which were studied for their vibrational characteristics using laser Doppler vibrometer. This study also helped me in designing some of the perception studies. Once we zeroed in on the piezoelectric actuator and we studied it using the laser Doppler vibrometer, we went ahead and looked into the smart headband design, which was then designed to be conductive, washable, flexible, as well as robust. The perception study conducted between on me and as well as my supervisors was also has also seen good preliminary results, which we will be then testing on the other human participants once COVID is better and we have the ethics for that. So thank you so much for listening, and please let me know if you have any questions.
Thank you very much, Pradipika. So and now let's have both talks open for questions.
Should I stop sharing?
Yes, please.
Okay.
That would be great. All right. Thank you so much. I can see that there will be, there could be a whole lot of linkage between telerehabilitation even and what you're working on, Pradipika. There's quite a bit of crossover. So that's quite nice. Let me start with a couple of questions while the audience gets warmed up to ask questions. Maybe I'll start with you, Kaelen. Just one general question. I wasn't familiar with the term adhesive capitis. Can you tell us what that is?
Yeah, just drawing from my kinesiology knowledge, it's also termed frozen shoulder. So I believe it's a inflammation of the joint itself. So it's it makes it very hard and difficult to move, and it makes it frozen essentially. And I believe it's to do with the ligaments. I might be wrong on that though.
Okay. Yeah. No, thanks for that. That was for my own knowledge. I didn't Google it while you're talking because I wanted to pay attention to you. So, but that's interesting to know. There's a question from Emily. Her question is to you, Kaelen, again. After your review of the available technologies, what gaps do you see in technology for shoulder assessments or other care of virtual health?
So the biggest gaps in knowledge is definitely the standardization of protocol, because almost every study I came across, it was done in a slightly different setting, and in a different population group, and many of them were in small studies, and many of them were pilot studies as well. So I think it's hard to compare the studies to each other because they were done completely different, and if the studies did take on their own standardized protocol, in terms of what shoulder kinematics they're going to measure, they're all done slightly differently. So it's hard to compile information to see which one could possibly not necessarily be the best, but it's hard to compare to each other and see if it's going to work on a grand scale because we just don't have that standardization of protocol yet. So I think future research definitely needs to go towards that.
Yeah, thanks, Kaelen, for that answer. One additional question that I had for you. So as you were reviewing the telerehab, I guess, assessment protocols, were you thinking of assessment protocols that would be used at, let's say, a local clinic, and then remotely the data will be obviously transmitted virtually to an expert in a central hub? Or were you referring to technologies that will be used at home as opposed to a local clinical center? So, and is there a difference between one environment versus the other in terms of the needs for these environments?
That's a really good question. I actually asked myself that a few times too. So I actually ended up including both of them in the review, just because a lot of the pilot studies I came across, they would do it in a clinical setting, and then they would say they could either virtually transmit it to a remote specialist somewhere, or it could be applied to the telemedicine context in the future. And that was the majority of the IMUs and the connects. And then there were a few at-home assessments with technology that was kind of designed for that. And there was a few more kind of hurdles to jump with that because it's at the home too. And so you're kind of relying on usability of the device. And you basically want it to be easiest to set up as possible. And it is also harder to build that rapport. And there's like a bit of like a psychological limitation to that I kind of went over. So yeah, there's two very different streams that I'm kind of looking at, and both have like their limitations and for sure, but very kind of different how you go about setting it up.
Very interesting. And as you said, telerehab is still in its infancy, and the ability to diagnose and assess, right, quantify, is really of paramount importance. So thanks for that work. I have some questions for you, Pradipika. I love that headband.
Thank you so much.
That's a great idea. And I was very impressed by the assessments that you have done all along to kind of determine where to place the sensors and the actuators and so on and so forth. There was one point that I missed, and that was related to the Parcinian corpuscle and the choice of frequency. So I think I understood it as we went forward. So you want to really activate the skin in such a way that will be, the most effective stimulus that would produce at a very small displacement of the skin, will produce a signal that can be sensed by the user. Is that correct?
Yes, that's correct.
So the Parcinian corpuscles don't need, so they get activated very quickly, with high frequency, and you don't need to move the skin, like the skin doesn't need to be displaced that much.
Yeah, at that frequency range of 200 to 250 hertz, we need a very small displacement. So that's also like something that's comfortable for the user, because we don't want something that has a very high displacement, because these people are going to be using are going to be using the headband for a long time, because they have like swallowing issues and everything. So usually, typically, the amount of time that they take for each meal is around like an hour or so. So we want something that's most comfortable for them as well. So yeah.
And you anticipate that the headband would be worn while they're eating. So that's the primary use for it. So it's not something that they would be wearing throughout the day. It's more when they are chewing. Is that
yes.
correct?
Yes.
Okay. So Michelle has a question. Can you talk about the sensor? Where would it be located? Does it interfere with eating?
So is that the sensor in the oral prosthesis?
Michelle, is that what you mean? Most likely. Yes.
Yeah, so I think it's inside the oral prosthesis. I'm not particularly sure. I don't think it will interfere with the eating process itself, but I'm not sure about the details, because that's not something that I worked on myself. But the oral prosthesis is just something that looks like sort of. So the picture that I'd shown on my slide, so it would just have sort of a structure and then, teeth-like structures. So the sensor would be sort of below, underneath. So it wouldn't interfere with eating. Yeah.
So these are, just to clarify, these are individuals who have lost their teeth for various reasons, and they're using an oral prosthesis now. So with the artificial teeth, right, as the way to chew their food. That's
yes.
Just to clarify, right? So within those, you could be within the artificial teeth or whatever in the bridge. You could be embedding some of these sensors. That's the idea, right?
Yeah.
Michelle, does that address your question? He's gonna type instead of saying.
Yeah. Hi.
Yeah. Okay.
Hello.
Yeah, it's much easier to just speak. So do these sensors currently exist, or are you planning on some kind of future development?
So yeah, go ahead, please.
No, you go ahead, please.
That work is being done by Dr. Daniel Alto in rehab medicine. So he's developing that oral prosthesis. So I'm not particularly sure, but I think the work is going on to develop these sensors and the oral prosthesis system as a whole as well.
Yeah, and when you used examples of bananas and cranberries, and I forget the other one, but you're basically looking for different textures of food, because I guess the main feedback is how much pressure you're putting on the prosthesis, right? So you want to signal the user when they're starting to approach a dangerous amount of pressure.
Yes.
All right. And do you have a separate signal for that?
That signal was acquired by sort of a system that Dr. Alto had developed for breaking food. So it was just like a load cell that they used, and it was a pneumatic system where they were using different food samples to break them, and then we captured those signals and I processed those, and that was used in the different studies that I was showing.
Yeah, I was referring more to your feedback signal. So if I'm putting too much pressure on my jaw, what sort of a signal would you send as a kind of a warning, just as opposed to this is a soft texture or crunchy or whatever? You want to send a signal saying stop chewing or stop chewing so hard.
Yeah, for that we will be using sinusoidal signals of different amplitudes. So when the amplitude goes higher, the intensity of the signal also increases. So that would alert the user that if they're using more force to chew.
Okay. Yeah.
And if I can just add a detail, I think it's more than just the amplitude that we want to provide to the user. It's also the texture. So that's in fact, because for amplitude, there could be some sort of simple, cheaper piezo, actuators that could be used. But really what we want to be able to provide is that sense of texture. So that's why we were using the signals that had been generated by Dr. Alto and his team, sort of artificially chewing through this different food. So they really chew through cranberry, or there's the system chews through cranberry, through toast, and recorded the measurement. And it's really to be able to transmit that sense of the texture in addition to the force by itself or the amplitude by itself, so that the person, in addition to be able to know if they're getting too high in terms of force, if they're going to break their teeth or bite their tongue, they also have a sense of what they're chewing. So with that texture, it gives them that information. So that's really what we wanted what we want to try to do.
Yeah, I think that's a really, really good sensor, really good theorem. I'm just thinking in terms of warning signal, like how do you really get somebody's attention that, wait a minute, you're at risk of breaking this. So
but in fact,
it's might be added or something.
But it's by the force that will be exerted on their skin. So there's some training, but by when they sense that the amplitude of the vibration gets too strong, then that's when they think, okay, I'm chewing too strong. So that's the idea.
So I know it's not easy to have tested on an actual person with this prosthesis in their mouth, but I'm wondering if they were able to separate, or do you think that there is the ability to separate between the textures and the force easily? So for the studies that you've done with your supervisors and yourself, I wasn't quite sure if I understood whether that was possible or not, to differentiate between force of chewing versus the texture of the food.
So we did do 2 different studies when it comes to the texture. So there was one study where we kept the amplitude of the breakage of the food. And then there was another study where we averaged we did a normalization method where we were averaging that energy. So it was just providing the signal was just providing information about textures. So even in that study, we had a high, percentage of correct answers. So I'm positive that, yeah.
But you didn't combine the two modes, the strength of chewing plus the texture in the same experiment.
We did. In the first experiment, we did with the force and the texture. The second experiment, we did only with the texture because we want to be sure that we are providing information only on the texture and they're able to differentiate between the texture based on the food texture actually and not just the force,
Got it. Okay. I was surprised that the toast and cranberry had not a very high differentiation. So it was almost close to the 50-50, kind of guesswork. I found that rather interesting because at least in my mind, I think they would have a different texture in my mouth. So that was, I found that a little bit interesting.
Yeah, I think the cranberry that was used was like dried cranberry.
Yeah.
Not the actual fruit. So I think they're very similar in terms of texture when it comes to that. Yes.
I see. Oh, good point.
Yeah.
Good point. Okay.
So it depends on the state of the food as well.
Of course. So that's very good. That's very good to know. So Yvonne has a question for you. Just to double check, is this a permanent prosthetic? If so, would this work while the patient is asleep if they had a history of teeth grinding?
So I think the prosthesis that they are talking about is the oral prosthesis, and I think it would be permanent. I'm not positive though, but the headband that we have that we have fabricated, that's not permanent. That's just to be worn during chewing.
Yeah. So I guess one could wonder whether there is something that could be similar to the headband, but maybe something that would, kind of alert the user that they're grinding their teeth. However, there are mouth guards for that. So I'm wondering whether that would be a better approach there, because I think when I'm asleep, I probably will ignore a lot of signals.
Yeah, I think during sleeping, I don't think that would be the most comfortable thing to have like signals. So that would disrupt sleep. So I guess a mouth guard is a better solution there.
Yeah. Okay, I have one last question, and that is about the textile itself. I like the, I'm looking at it as being a smart textile, and I understand that the sensors or the actuators in it are part of what makes it smart. But is the garment itself, does that have intelligence in it?
The garment itself, no. So I think there's different kinds of smart textiles. So there's textiles where we have integrated functions where you could integrate that kind of function and it would adapt. But in this case, it's hard to sort of integrate that function as well as communicate with like a device and send those signals that we want to send. So we just sort of have the fabric structure, and then we used a Velcro system in order to integrate the electronic components. But I think going forward, there can be improvements where we are, where we have conductive yarns that are going through the textile, and yeah.
Nice.